Okay, thank you for that introduction. I get the impression this will be a slightly different talk to some of the others that you might have heard, in that I'm not going to talk about the research. I'm going to talk about the meta problem, which is how you support the researchers in handling the massive data sets. So they analyze them, but sort of, okay, my current role in the database service group isn't relevant to that, but a past role in managing the data center and managing the compute farms we had was very relevant. I'm going to talk to you about the problems that we had for that, managing the compute farms and supporting the people doing the work. So given the time constraints, I will not talk about physics. I'll talk a bit about the challenge, our technique, go through that in outline, then in detail. Some pointers towards things that we are looking at now to implement in a couple of years' time, and then quickly summarize. So the challenge really is, okay, so I'm going to talk a bit about physics. This is a standard model which is quite well understood, but there are missing things like why is the origin of mass, particular difference between photons and the W and Z particles. We had astronomy talks, dark energy was mentioned, but I didn't hear dark matter. Dark matter, there could be partners of these matter particles. One of those superparticles will be stable. That will be a candidate for dark matter in the universe. So there are a number of things that we want to understand about that. And to understand it, we need to look at very rare processes. If you collide protons together at our sort of energies, then you get an awful lot of dross. So this is based on the 2010 data, 3 trillion events overall, only 750 of the interesting Higgs ones. So looking for the particles down here is very difficult. You have to collect a lot of data. Now clearly the experiments try and throw away huge amounts of this dross. So they turn petabytes, a data rate of a petabyte a second, into a few hundred megabytes a second. But even so, we have to search for through a lot of data to find these things that are interesting. So basically, the 4 LHC experiments, Atlas and CMS, the general purpose ones, ALICE and LHCb looking for something specialist things. In particular, LHCb looks at why there's no antimatter in the universe. These all generate huge amounts of data. 40 million collisions a second, as I said, a petabyte of data produced in the heart of the accelerator. But it gets down to a few hundred events a second that look like this. Recorded on tape. Now the prediction was once upon a time 15 petabytes a year. If you actually look, the current forecast is 20 to 25 petabytes a year. And here is proof that over the past year we've recorded a bit more than 25 petabytes. And at the moment we're recording above a petabyte a week in some occasions. Now this is interesting. They've jumped up there because we're about to shut down for a couple of, 18 months to go up to our design energy. And so there'll be no data taken next year. So what the experiments are doing is out of that huge amount of data they take each second, they're taking some and stashing it away in a corner, and they're not looking at it this year. They'll start looking at it next year when there's no data coming out of the accelerator. So that's a nice sort of wheeze for them, but it means that we have to handle data rates above the levels they told us they wanted a year ago. They, on the other hand, have to handle problems that the collider gives them. I'll come to that in a minute. So, they have the computational problem is to go from the messy picture there to the clean Higgs signal there. But actually, to get the data rates that they want to generate all the events, this is really the clean signal. So this is 25 clean signals like that in one bunch crossing. And you can imagine how complex the complex signal is that they have to do for that. So there's an enormous amount of data volume and enormous processing power is needed to deliver that. So what's our technique? Well, I'm insisting on this because I read the synopsis and we're supposed to explore novel techniques. So what is our technique? Well, it's actually quite good because yesterday divide and conquer was mentioned a lot. So I think I'll call it that. So we break up a massive data set. So that's a CD stack with 15 petabytes a year of data. So we're above a balloon with 25 petabytes of data. Send it around the world. And here This is CERN as a tier 0 producing the data, and with around 10, 11 tier 1s around the world, we have the custodial role. The tier 0 and tier 1s have large tape robot facilities and store the data in multiple copies. So if we lose part of the data at CERN, we can recover it from one of the tier 1s around the world. And that's complemented by over 100 tier 2 centers that don't have the data curation role, but they do provide valuable CPU and data facilities for the experiments. We then analyze the data in parallel across those centers, and this is a trace from January to July this year of the data of the number of jobs that are running processing the data. So there's 100K average across the year. But if you look over the past few months, I think you can convince yourself it's 120, 130,000 jobs that are running in parallel around the clock, analyzing the data. And this is just for Atlas, okay? There is also CMS running their 130,000 jobs, plus another 100,000 or so from LHCb. So there's a lot of data spread around the world and a lot of jobs analyzing that around the world. You gather the results together, and you discover the Higgs. So the Higgs got a mention for somebody that was asking earlier. A Higgs, because this is what we have to discover later. The introduction said strong evidence. Our Director General says we've discovered it, and I'm not going to disagree. The only thing is...
Your press statement.
Well, I'll read it again. Anyway, the interesting thing, is it the standard model Higgs, or is it the supersymmetric Higgs, in which case the properties will be slightly different, and there will be a few more. This is certainly a nice result, but, is it novel? Divide and conquer was mentioned yesterday, and so on, and it's been around a while. Well, the technique itself maybe not, but the implementation, I would claim certainly is. This is terascale computing. Note the two R's there. The amazing thing coming to the press release is that the computing got explicit thanks from the spokespeople of the Atlas and CMS experiments and from our Director General. So these are the slides that were shown during the July the 4th event announcing the discovery. It's actually amazing that the grid computing that we have, that we've put in place, gets the thanks for that. And Fabiola Gianotti, who produced this chart in 2004-05, said that her big worry about grid computing would be that it would get in the way. Now, that was understandable as a worry, but it's very nice to see her coming back 4 or 5 years later and saying how wonderful we are to actually help them the physicists produce the results. So, skimming through now in more detail, what was planned and how did reality happen. The main thing that came out is this. When we were preparing for this, is the book from Foster and Kesselman's came out, which really showed how we could tie together worldwide facilities. We could perhaps have installed some massive computing like the Blue Gene Q that you saw at CERN, but that would have been a huge upgrade in terms of our facilities. As it was, I had to oversee an upgrade, and we're doing another one now. Whether we could have afforded the millions of dollars of electricity, I don't know. But instead, we used these techniques to basically, in terms of the WLCG, the CERN-focused project, to deploy a grid which worked to do the physics. Meanwhile, other people, developed the software and the techniques. So the techniques really that you need 3 things to provide a grid. You need a compute element, which is a snazzy name for an interface to the local batch scheduler at a site. So we at CERN use platforms that are now IBM's LSF. Sun Grid Engine, Oracle Grid Engine is another one. Slurm, another, PBS, various ones. But there has to be a standard interface, and this is the compute element. You have a standard interface similarly to the mass storage system at a site. And then you have a resource broker. So I send my jobs to the resource broker. It looks at the data I want to analyze, how much CPU time I need, and then sends it to an appropriate site. So that was the principle, and that's what we started off with. But fairly soon we came up against and many implementations of these basic principles, which again, actually, as WLCG, we had to deal with that. We had to have an interoperation between the European middleware, the Nordic middleware, which is different, and then the US middleware. So apart from that complexity, another issue is that grid sites generally want to keep their CPUs busy. They've bought these, thousands, hundreds, millions of dollars worth of CPUs, and they want to show their funding agencies that they're being used all the time, and that therefore they can buy more next year. They need to buy more next year. On the other hand, and they do that by keeping a queue of work that's available. So as soon as any CPU becomes free, they need to have a job that they can slot in immediately and start to use that time. But on the other hand, the users, they're interested in making sure that their job starts as soon as possible. So if I send my site to Slack, which is a tier 2 for Atlas, and it's in the queue there, but Brookhaven, which is a tier 1 for Atlas, happens to get the work slot free first, and your job runs there, then I'm not going to be very happy. So there's a conflict between the desires of sites to keep things free, to keep things busy, and users to have quick turnaround. So moving away from the nice model, our experiments came up with this idea of a pilot job framework. So there, it's the experiment that sends the work to the sites with a special pilot job, and I send my work to a central queue. And when the experiment's pilot job starts at any site, whether it's Slack or Brookhaven, it will look to see who's the first job in the queue, and if it's mine, it will run that at Brookhaven and not at Slack. So this sort of separates out the site role and the experiment desires, but on the other hand, it sort of breaks the nice grid model. It removes the resource broker, which is still in use for other communities that are using the grid. And rather than having one nice framework, we have 4, because all of the 4 experiments have a specific pilot job framework. Now, there's no reason why they did, but they all developed it separately, and we'll have to see in future if that merges together. Okay, data. We have to worry about at CERN about long-term storage. We have to worry at CERN about sending it out to the tier 1s, and then everybody has to worry about distributing the data. And then also we have to worry about metadata distribution, and I'll come to that a bit later. So these are some sort of versions of the data rates, probably last year's. I think we're getting in more like 1.2 to 1.3 petabytes a second now, and this will have impacts on the data which is going to our storage and out to the rest of the world. So these are fairly large data rates that we have to handle. A quick talk about the mass storage systems. We developed a couple at CERN and Dcache at DAISY. These were adapted to the data rates that we needed. And also, point I'll come to later, which is that Dcache is used as a disk storage manager at the tier 2s. They don't need to manage tape, and they can use Dcache for that. There's an interesting twist that I'll come to in a minute on a point about Castor not having that disk-only functionality. Okay, just a quick word about tape. We might have a massive data set overall, but it's made up of huge numbers of small files. This is a sort of distribution with a sort of log type scale on the bottom, which means that the file size overall is around 200 megabytes, 300. It's gone up maybe a bit now to a bit more, but still it's way below the level at which you get optimum use of the tape drives that are capable of 120, 150 megabytes a second. If you're operating down here, they're running at maybe 40, 50, which is way below the performance. So it's not good for us. We need to have more expensive tape drives, and it's certainly not good for the drives because they keep starting and stopping. So the model there is that we have to change the way in which we operate. Rather than synchronizing the tape files with each file, we have to synchronize and change the tape driver to synchronize with a given amount of data that's written. And doing that, we can achieve neat performance on the drives there. So putting that into place last year it was done, and it's in production really for this year, has dramatically changed the number of tape drives we need. We haven't needed to buy any tape drives this year. Okay, another interesting point about tapes is that if you want to accept data efficiently at these data rates, then you have a large number of disk servers accepting the data in parallel. And then when they're full, one of those will connect to a tape drive and stream all of its data out to that tape. So this has the net effect that data that's recorded at the same time is spread across many tapes, because it's gone in parallel to many servers, and those servers have written it out to different tapes. But when people read data back, they've got this annoying habit of wanting to read data that was written at the same time. They're not willing to read all of the data that they get off one tape and say, okay, I'll process that. They want to read the data that was recorded today or yesterday. And that's spread, of course, across many tapes. And the optimized way to do it is write today's data on a small number of tapes, but then you get inefficient data writing. So this leads to a conflict in terms of the performance of the overall system. And believe it or not, what we have to do then is stop users using tape. We developed these nice mass storage systems which are supposed to be able to recall data from tape if people need it, but we have to stop them doing that and move to a completely separate analysis disk pool which is managed separately. And then the experiments are responsible for taking the data which they think people want to analyze and copying it to this disk pool over here, where it's then safe and separate, and these people up here can't access the tapes. Now, this is a problem for a PhD student who wants to check something after the Viva for his PhD or her PhD, when it's no longer a popular data set, so it's been moved off the tape, but it certainly makes the whole system work a lot better. And the other point about this is that the disk pool here has to be very reliable. You're taking the data in from the experiment, and you certainly don't want to lose it. The disk pool here can be much less reliable. The data, if you need to, can be recalled from tape, and it doesn't really matter because there's some other data that people can analyze anyway. This is another point I'll come back to in a minute. Okay, so this is a picture showing how we've moved from the caster system to, which is the tape-only system, or the tape-back system, into an increasing amount on the disk-only system. And here for Atlas, similarly, you can see that there's a bigger increase this year. All the new disk has gone into the analysis pool, and but we've kept a buffer for taking in the tape from the experiment, the data from the experiment. Okay. In terms of data distribution, you then have an interesting problem in that, I touched earlier on the fact that sites want to do things in the way that they allocate CPU. So if a site is 50% of its time is dedicated to Atlas, a quarter to CMS, and the rest to ALICE and LHCb, they don't want to see the network connection that they have being saturated by LHCb if it stops them receiving data from Atlas. So we develop a file transfer system to manage the bandwidth for that, and also so that any network failures or remote system failures during the transfer were hidden from me. So this is a necessary thing is shown, I think, by the fact that Globus last year or whenever, I think it was last year, when they moved from the Globus toolkit, which is a toolkit for grid builders, they sort of came up with cloud services that they could have to support researchers. And one of the things they developed is a fast, powerful file transfer service that's easy to use. No need to babysit your job or worry about coming back to a failed request. So the things that we developed a few years ago are coming as more basic services, and perhaps we can switch to those in future and avoid having our own dedicated code. Now, in order to work, I mentioned the sort of caster mass storage system at CERN, the Dcache one at DAISY, and there are a few others around the place. Now, if you're writing a generic service, you don't want to have that know about all of the different mass storage systems. So we have an abstract interface to storage, FTS codes against that, and each storage system implements that interface, and everything should work. Now, this is a good idea, certainly, but the problem is that the storage resource manager interface that we use, I think turns out not to be a generic, perfectly generic, complete abstraction layer. And it also turns out that there are some very fundamental decisions that you can make when you're writing a mass storage system that it's extremely hard to hide and pretend that they don't exist. So this doesn't quite work. And we have a lot of interest now in looking at other people's storage interfaces, so Amazon S3 or whatever. These don't try to be as complete as the SRM, which I think the interest actually came from, the initial interest of that was from Berkeley, by the way. So this doesn't try to be as complete, but if we can use it, then we should certainly try to do that, again, to simplify the sort of things that we're doing. Okay, point there that you also need to catalog the data, but I'll skip over that probably because there's no clock here, but I suspect I'm running over time. A more interesting point, though, comes back again to the, some of the things I was saying about the disk failure rates and the analysis pool, and the way people operate and mass storage systems. So we said that the mass storage system, we've gone away from the model where you will have the mass storage system recover data from tape if people want to use it, to a one where you place data. Now, when we all started a few years ago, 2-3 years ago, the experiments very carefully decided that they would allocate data sets to the tier 1s and to the tier 2s. They came out with their own algorithms for doing that, and it was to share out data according to people's research interests. It was to make sure that data was balanced geographically around different places, so that there were copies of the data sets in North America, in Europe, and all sorts of wonderful equalization things. What they found, though, is that people really don't evenly spread their interest in data sets. There's 2 or 3 data sets that are hammered on, and a vast majority that are only used if you want to scan over the whole data. And so what you saw here, I forget exactly what the scales are, okay, data set ID and how frequently it's accessed. So you can see that there's a really very steep curve between the most frequently accessed data set and ones which are rarely accessed. And CMS has 8 orders of magnitude, they claim, between the frequently and the least frequently accessed one. So rather than having the same static access, we've moved to one which is dynamic. I'm that much out of time. Okay, so we create automatically copies of data at multiple sites. So then, going back to my point here, network capacity is much more available now than it was, we imagined it would be when we started off. So it's reliable as well. And so the idea now is let's recover data from another site if it's not available, or if the disk has failed. Okay. So one interesting point. So we have a thing about distributing metadata, which is partly in an Oracle database. And there again, we have the problem that we're not a company and can tell people what to do at remote sites. So we had to use non-optimal technology from Oracle, which we worked with Oracle to vastly improve the performance of. Another interesting point is that you have to make sure that the libraries that you have, the software libraries, are up to date at each site. And we had lots of problems with doing that. So somebody developed a neat idea of a global caching file system called CERN VMFS, which uses HTTP SQUID caches to have a cache of the files on each execution node. And you can see that if you have NFS as a shared file system, running jobs in parallel at a site, you get delays. If you're having CVMFS, then there's an initial delay as the local caches are loaded, and then after that, the number of jobs that you have running in parallel has no impact on that. So this is also very neat in terms of compressing the volume and the number of files that are distributed, because as a library changes, most of the software doesn't. So Atlas at the moment, there's only 1.8 million distinct files out of some 22, and you have a factor of 6 in the compression for files that you distribute. Okay, towards the future, I'll skip this. Clouds, I'll just say that we're very well adapted to that. I don't see clouds as replacing the grid that we have. I see rather that what we want to do and what we're looking at the moment is to develop cloud interfaces to, if you like, as a compute element. And then if you want to run stuff commercially, either directly from the experiment or from sites, you'll be able to. So we'll have a grid of clouds serving our users. And one last interesting point is on identity management. I think this is very interesting for our community, and it's spreading out of that now, is that none of this model works without trust. Today, I submit a job to the grid. It arrives at your site, and you don't know me, you've never met me, and you don't know that if I am abusing your resources, that you can get back and tell me off. So why do you do that? And the answer is that we've set up this trust federation between certificate authorities around the world, so Asia Pacific, EU, and the Americas, which means that I have a certificate from one site, all of these people trust each other, and so your site believes that there will be a chain of trust so you can run my job anonymously. We're faced with a problem now going beyond that, in that that's fine for running jobs, but say there's a repository of information at your site that I want to edit. That you're not going to let people do anonymously. So we have the problem that people need identities at every site, or some people need identities at every site around the grid to be able to do this, to edit information as an identified person, not as an anonymous person. And we need, and not alone want, need to move away from that to a federated identity system, where somebody has their identity at Brookhaven, and they use that identity at CERN to update the resources to edit files, and rather than having to, first of all, get an account at CERN and then worry about maintaining that. And this, as I said, is something which is becoming of interest to a wide range of other communities now to build this federated identity system. Okay, so the summary, the WLCG has delivered the capability to manage the volumes. The excellent performance has enabled physicists to deliver that. Some of the techniques are maybe not novel, but in the fact that we've built this world's largest multi-community open scientific grid is actually quite amazing. We've addressed the practical problems that we've had in terms of handling the large-scale data storage, distribution, and access. And we've built a global trust federation to enable people to do that and to work collaboratively in an open world without regard to national boundaries. Thank you.